Well, hello everyone, and welcome to another Starin AV Meetup Coffee Break. The term AV Meetup comes from our local in-person events where we've taken folks from San Francisco to Boston to Chicago, Philadelphia, and other large markets out on boat trips. We've shown some systems in the process, and it's been a lot of fun. The AV Meetup on the web has two versions. The Coffee Break, wherein under the time it takes to sip a cup of Java, we cover application-driven topics, and then the second version is the workshop that goes deep into the subject over the course of an hour. Today, of course, is a workshop. Now, note during the presentation we've muted mics to keep the noise floor down, so for questions, please use the chat window, and we'll address all those at the end. Stay with us to get your super cool AV over IP t-shirt. Yes, you're part of the beginning of our series on network solutions, and it's your responsibility to show the world that you know AV over IP with your t-shirt. So make sure that we have your size if you haven't given it to us in the registration process. I'm pleased to announce the location of our first live session, 3-day workshop with Professor Phil at Cincinnati, Ohio. And it's going to be on July 28th, 29th, and 30th, which is a Tuesday, Wednesday, and Thursday. And anybody from that area knows that city is about 100 miles from 5 major markets in 3 states, so we should have a great turnout. We're looking at a price point of about $700 per person for individuals, and then there's a team person price that we're looking at about $600 per person. So obviously the price gets better with the more team members that you bring in from your company. So let us know in the chat window in the questions pane if you'd be interested, because I think that that location is going to be filling up soon, and obviously we're going to have a lot more of these throughout the summer and the fall in places that are even closer to your home. Remember, that price does include breakfast and lunches and CTS credits, which are always important. We're going to send out flyers after today's presentation, and of course we'll keep you all posted more locations this summer and fall. I want to introduce our speaker. Phil Hippensteel is a professor, researcher, writer, and consultant that's worked in both the AV and the IT industries. As a teacher, he spent over 40 years in higher education, and he finished his full-time career at Penn State, where he currently teaches part-time. Over 3 decades, he has taught nearly 12,000 students across 27 states. That still blows me away. He is an active researcher working on IP video transport and network performance. For 4 years, he wrote a column called Ask Professor Phil for AV Technology magazine. And his column has just been modified to be a tutorial series entitled Professor Phil's Bite-Sized Lesson, and that's bite with a Y. He has also written dozens of feature articles for AV Technology, Information Week, and Network World magazines. So, without any further delay, Professor Phil, take it away.
Thanks, Neil. Each time I've started one of these webinars, I've tried to kind of set the stage for the topics we're going to cover, and I'd like to do that with today's topics. In my opinion, it was IPTV that really began the migration of the AV industry into IP. It took about 7 years for the telecommunications industry to realize that quality voice could be done using TCP/IP. There were some naysayers in the beginning. But after the AV industry studied that fact, they began to believe that it would be possible to do video in the same way over TCP/IP. And so the video transport might be possible, and as a result, the MPEG group got together and came up with a specification called transport mechanism, which they ultimately called MPEG transport. Then the service providers got in the act, AT&T, Verizon, Comcast, Time Warner, and those fellows, and they were the first to embrace MPEG transport, and they discovered it really worked well. It worked very efficiently. That was around 2004, 2005. In fact, in 2005, I remember I taught the first IPTV cast class to Comcast that year in Philadelphia. Then in order to reduce the total bandwidth that video was sending to the receivers, multicast addressing was introduced. Multicast had been around for a while, but multicast was something that, even though it was available, hadn't been used very much, and IPTV was the first big application which made efficient use of it. Multicasting can really be tricky. It can be tricky to deploy, it can be tricky to understand, so it's a good idea to have some idea of what issues you or your customer might encounter when you try to use multicasting. Now, one last comment about studying video over IP technology. When the VoIP revolution began, as I mentioned, there were a lot of naysayers who said it's never going to be toll quality. It's just never going to be quite toll quality. Well, today, voice over IP is better than toll quality. In fact, in a video conference, the bandwidth typically carried today is 22 kilohertz, which is higher than the telephone system carries, which is 64 kilohertz. So it's an enhanced quality, above toll quality. And in fact, it's extremely good quality. There is absolutely no reason to believe that the same kind of advancement with video can't happen when we do video over IP. So this thing we call IPTV, there's a good bit of confusion in the industry about what the term means. But the consensus should be rather clear that IPTV, by this time, the consensus is that IPTV is video that's using UDP traffic and that the payload is the MPEG transport payload. IPTV is being heavily used by the carriers. They discovered that it was really just an advanced form of statistical multiplexing, which had been done by the telecommunications industry for 25 years. In the enterprise, it's mostly used at this point in 3 applications. It's used in hospitals and schools. In hospitals, it allows data screens for ordering meals and for listing events that are in the hospital and things like that to be incorporated in with training videos and with the entertainment channels that probably come in from the satellite or the cable company. In schools, it allows delivery of video over twisted pair cable structure, over the twisted pair cable structure, while at the same time that cable structure can be used to connect to the internet. But the area that's really new is that MPEG transport is gaining very rapid acceleration in digital signage. But why would somebody prefer IP transport over straight digital transport in an application such as digital signage? Well, for one thing, the displays can be anywhere the network can reach. The displays can be in other buildings or other campuses or even other countries. And in our next slide, we'll see that it is, in fact, an exact replacement with those benefits over the traditional coax system. So a convenient way to look at IPTV is to see it as a replacement for the traditional coax system. In the coax system, we had sources, typically analog or digital, that came into a head end. They get modulated onto a channel, like channel 6 or channel 12 or channel 22. The channels are all sent simultaneously out over a hybrid fiber coax cable plant. At each splitter, the signal is amplified back up so that it's ready to be received by any TV that might be attached, and it's delivered to the TV. IPTV, while it has essentially the same architecture, takes the inputs, puts them into encoders, which digitize the stream if it isn't already digital, digitizes the stream, compresses, packetizes it. The TCP/IP stack places that information in IP packets. They're sent out over the IP network, and they're received by a set-top box, which is attached to a TV, or if the TV has a set-top box built in, so-called smart set-top box, smart TVs, the process is reversed and the information is displayed on the screen. So how does MPEG-2 transport work? This is what comes from the committee which created MPEG-2 and created MPEG-4. There are actually 2 different versions of MPEG transport, one that came from the MPEG-2 group and one that came from the MPEG-4 group. But the subtle differences between the 2 are not important for our purposes. So we're going to take a look at them together. The first thing that happens is that the analog and digital video is digitized first. By the way, I show here 2 streams, but typically there are 4. There's usually video 1, audio 2, and a control stream. First thing that happens is that they are digitized. Then they're blocked off into packets. The packets are multiplexed together, or muxed together, multiplexed together, and they're put into an IP program stream, into either a stream carrying 1 channel or a stream carrying multiple channels with IP addresses attached to them, and they're delivered out to the network. When they arrive at the receiver, the process is reversed. They are first demultiplexed, then depacketized back into a stream, then uncompressed back into the video or the audio that's to be played out. The key to the MPEG transport stream are what are referred to as MPEG transport packets. Packets like this that contain all of the information that's needed to the metadata and the actual audio and video data. Each one of these packets is 184 bytes of data that's audio or video or control, and a 4-byte transport header that's attached to it, making a total of 188 bytes. Now, if you've been in any TCP/IP class before, you know that that's not a very big packet. In fact, typically you can get 7 of these in an IP packet. But the 184 bytes of data is prefixed with a 4-byte header. I'll tell you a little bit more about what's in that header in succeeding slides. And that makes what is called an MPEG transport packet, or just a transport packet. Typically 7 of these go inside of one IP packet. Now in some rare instances, typically about 1 out of every 300 or 400 packets, the packet structure will be slightly changed, and they'll use what's called an extended header. The extended header is used when they want to send something called a program allocation table or a program map table that shows within the overall stream what channels are running on what numbers and how those channels are broken down as far as whether they have 1 audio, 2 audios, 5 audios, and so forth. That kind of information would be sent periodically across the network. But the vast majority of the packets will look like this: 4 bytes of header, 188 bytes of payload. Now, to understand how MPEG transport works, a really critical part of it is to understand how the framing is compressed. That is, the individual frames that are sent are typically sent at 30 frames per second or 60 frames per second, occasionally 15 frames per second. When they are compressed by the MPEG compression process, they'll be compressed into one of 3 types of frames. The largest frame type is called an iframe. Basically, an iframe is a JPEG image. The compression process takes the screen, breaks it down into blocks that are usually 8 pixels by 8 pixels or multiples of 8 pixels by 8 pixels, like 16 by 16 and so forth, compresses that information and creates essentially what we would think of as a JPEG image. Then after that iframe is created, the encoder estimates based on that iframe what the image is going to look like a small portion of the second later, like 4/30ths of a second later. And it predicts what the information is going to look like on the screen. And it creates this frame, which is really the difference between what it thinks it's going to look like and what it actually measured it to look like. That's called a predictive frame or a P frame. P frames are smaller. We'll call them medium-sized frames. After it has an iframe and it predicts a P frame, then it estimates by simply averaging 1 or 2 or 3 or more intermediate frames called B frames, bidirectional frames. So the structure becomes a fully measured screen, a fully measured estimated screen, a predicted screen, and 2 that are the average of these 2. That process is repeated and repeated and repeated, and that's the information that's sent. So we end up with iframes that are very large, typically hundreds and maybe even, well, typically more likely, even thousands of IP packets to describe one iframe. P frames that are medium size, which will take a couple hundred packets to describe a P frame, and B frames that can be less than 100 packets, but typically are someplace in the 60 to 100 packet range, depending upon the complexity of the image and some other factors. The sequence of compressed frames starting at an iframe and ending just before the next iframe is called a GOP, a group of pictures, a GOP. And very often in the encoder, you have to choose the GOP. So for example, here we're sending I, BBP, 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 and then another iframe. This is a full measurement of the image. This is a full measurement of the image. The group of pictures are all of the estimates and the measurement of the image in the beginning here. All of these form what's called a group of pictures, or the GOP. So here's what's happening inside the encoder. We're going to talk about what happens with what's called a single program transport stream. This would be one image being sent to one decoder. The video encoder and the audio encoder first compress the information. The audio encoder might compress it, for example, into AAC or into MP3. The video encoder is going to compress it into MPEG-2 or MPEG-4 H.264. Let's say it's compressing into MPEG-2. It's going to create the I frames, B frames, and the P frames. Then it's going to break both of those data streams down into blocks of 184 bytes each. Here you probably have several hundred to 1,000. Here you might have somewhere up around 100. Here you probably have 150, 200, 300. and multiplex them together after you've placed a header for the stream and then individual 4-byte headers that go in front of each block of data. Now, what's inside of here is relatively important. They're going to put a timestamp in here for when this information is to be presented. So if, for example, these two both came from this iframe, of course, they'd be presented to the user at the same time. So the timestamp in here would match the timestamp in here. They'll also put something in here called a continuity counter, just a little rolling index that goes 0 through 15, 0 through 15, 0 through 15, so that if one of these little babies get lost, the decoder knows that there's something missing and can take some kind of corrective action if the code in the decoder is sophisticated enough to know what to do about it. So after that's done, then we build an IP packet. And we build the IP packet by putting 7 of these transport packets inside of one IP packet. Since each of them is 188 bytes long, 7 times 188 is 1316. We end up with 1316 bytes of data. We can use an optional RTP header. We talked about RTP in the seminar on TCP versus UDP. We can put an optional RTP header in here, put an 8-byte UDP header in, put the IP header on, put the Ethernet header on, and boom, we've got a TCP IP packet to send out in the network. So when is RTP used? It turns out that RTP is being used primarily in enterprise applications, hospitals, digital signage, places like that, security cameras, but it's very rarely used by carriers. They see it as extra overhead because all of the timing information for presentation and synchronization is already in here, so they don't use it. Here you see that we've got 6 video packets and 1 audio packet. It's fairly typical to have about 5 video packets, 1 audio packet, and 1 control packet. But it is a mixture of different audio and video transport packets. And incidentally, in a single transport stream, these would all come from one program. But if you were transmitting 3 or 4 channels, they could easily be mixed from different channels. So I used a packet sniffer and grabbed some packets off of an MPEG transmission system. And it's interesting to look at this and see what the sniffer is telling us. These are the packets 1, 2, 3, 4, 5, 6, 7, and so forth. Here's the absolute timestamp from when it started to capture. You can see here this is 33 microseconds after this packet was sent. This is about 150 microseconds later and so forth. This one is being sent from the source 1.54. This one from the source 50.2, so they're coming from 2 different encoders. This one's being sent to a multicast address, 226.241. This one's being sent to 226.141, so they're going to different decoders. So you can see it's a highly multiplexed set of packets going from different sources to different destinations. This is not typical of, for example, digital signage. Well, it could be digital signage, but this wouldn't be typical, for example, of where you were sending from a single device as a source to a single receiver. This actually came out of a carrier network. This came out of a very small carrier network. Roughly, this telephone company was about the size of a large university. And this would be fairly typical for a pretty big university. If we take a look at the detail of this multicast packet here, down here you can see the Ethernet header and the IP header, the UDP that's being used. You can see that RTP is not being used. And here are the 7 little transport packets. Wireshark, which I used here, Wireshark actually decodes it. And it tells us that this is an MPEG transport packet following the ISO standard, and that this has a continuity counter of 14, and it's on PID 31, PID hexadecimal 31. PID is program identifier. Each individual elementary stream, be it audio or video or control, runs on a different PID number. So this particular MPEG transport packet here is part of the same audio or video or control that this one down here is and this one here is. So you can see here the continuity counter on PID 31 goes 0 and then 1. And then it jumps over to a different stream and says, I'm at continuity counter 9. And by using this continuity counter, it can keep track of whether or not within each one of these program streams here, any of the information has been dropped. This is another example that was pulled out of that same network. They had a real problem with distortion of the signal, a very bad distortion of the signal. And you can see down here that Wireshark is telling me that we've skipped some continuity counters. What we discovered was that the encoder that they were using in the company was miswriting this field. The field was being incorrectly recorded, and these numbers were completely erroneous. And they actually had to go back and change the firmware in the encoders to get it fixed. It took a while to find it, but it was possible to find it just using Wireshark and having a knowledge of how MPEG transport works. So if we take a look at a typical encoder, this is an AdTech encoder, and here we're picking the choice for how we want the video to be transported. And you can see that our input's SDI input, and we've asked for it to be compressed H.264 using a chroma pattern of 422, which you probably know or may know that is what is typically used in a studio application. Down here we say that we want the GOP to be 15 frames long, which means that we will send a group of pictures every half second at 30 frames per second. And we've actually picked a GOP structure to be I, BBP, 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 until it hits the 15th frame, which will be an I again. You can see that there are other choices for the GOP structure. Here I could have picked what's covered up here with this pull-down menu is I. I can pick I, in other words, only I frames, or I can pick IP, which would give us the pattern IP, 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 IP. We can pick IBP, and we can pick IBBP. And as we go from all I's to IP to IBBP to IBBP and so forth, we are reducing the amount of bandwidth we're going to use because each of these becomes more and more compressed. Now, what's the disadvantage to compressing it more? The disadvantage to compressing it more is that, for example, in this case here, I get a full representation of what's on the screen every other frame. In other words, every 15th of a second. Here, where the iframe appears on the 1st, 4th, 7th, and so forth, I get a representation roughly about every 7th of a second. Here, with a GOP structure of 15, I would only get an iframe every half second, and as a result, any distortion that would happen in this frame here, any information that might be distorted here, which will affect all of the frames that follow it until we get to the next I. It's only the iframe that recorrects or makes a new measurement of what's in the screen. So the trade-off is, as you go this way, decrease bandwidth, but as you go this way, you get improved overall quality, especially in the presence of errors. So, how do network errors affect IPTV? When I did the class for Comcast way back in 2004, 2005, 2006, I don't remember exactly which year it was, the fellow who was asking me to put the class together kept saying, if you can just explain tiling, if you can just explain tiling. To understand why tiling happens, you have to understand basically the way in which the IP and B frames are built. As I mentioned once before, it's all based on taking blocks of pixels, 8 by 8 or multiples of 8 by 8, and compressing those, and then after those are compressed, using succeeding blocks after that as estimates or as differences with the first block that was in this particular group. So we call something like this where these blocks are based on this block, we call this a slice. The slice can be small like this, it can be half the width of the screen, it can be an entire length of the screen, sometimes it's even more than one row in the screen. But that's called a slice. So when you drop a single packet, you might be dropping just the information that affects, for example, in a B frame, just affects this one block. But you might be dropping information that affects a group of blocks, and as a result, you get a distorted slice. So what I'm going to do is show you a quick video. And in the video on the left-hand side here, when I play it, you're going to see that the network has dropped 1 out of every 200 packets. 1 out of every 200 packets. And what you want to watch for is a little distortion up in here and then a little distortion over in here. And notice that the distortion is noticeable, but not real significant. It would not be acceptable, but at the same time, it doesn't destroy the picture. So let's take a look at this real short clip. So you saw a little bit of distortion there. It was random all over the screen. It was noticeable, but it wasn't something that would keep you from understanding what was going on the screen. That's one frame dropped randomly per 200 frames transmitted. Now here we're going to drop 5% of the information, and you'll see that the distortion is much more noticeable in terms of color, in terms of frequency. Everything is much worse. That's called toweling, and the toweling happens because of the fact that everything is based on compressing small blocks of information that are in the screen and succeeding blocks that follow along behind them in what's called a slice. I pulled out one video frame that was in a video. This is what the JPEG image or the iframe looked like. This is what the frame looked like when I took out 2 MPEG transport packets, just 2. That would be roughly half of an IP packet. And you can see here, there's some distortion here. And the distortion goes to the end of the slice, which is at the end of that line. The distortion is not that far off in terms of color from where it was here, because we kept most of the information, only lost a little bit. But then when I dropped 4 MPEG transport packets, you see here, it happened to hit up here. We lost everything except the average intensity. We lost everything except the average brightness, the gray. So the effect will be random, but it always looks like a tile or a slice. That's the impact that IP network loss has on MPEG transport when it is transmitted with UDP. But MPEG transport appears in other places, and I just pulled this off of the Apple Developers Network down here. Here's the link if you want to take a look at it and get more information about it. All of the forms of adaptive streaming now use MPEG transport: Apple HLS, Microsoft Smooth Streaming, Adobe HDS, and so-called Dash. All of those adaptive streaming methods now use MPEG transport. You can see here in Apple's diagram, the encoder creates the MPEG transport stream, segments it, places different profiles on the server, then through something called a manifest file, which is really an index file, the client says, hey, I would like this chunk here, and then I'd like to follow it by a nicer chunk in the next video that I look at because my network's improving and so forth. So these are different profiles of video here, all of which have been created as different MPEG transport streams and stored on the server to be retrieved with HTTP in an adaptive streaming method. Now I'm going to make you think a little bit. The errors here will not look like the errors we saw in IPTV, even though we're using MPEG transport. Why not? Well, if you sat in on the second webinar that we did, which was about TCP versus UDP, this is TCP traffic. If it doesn't get there, it's retransmitted. So the errors will be fixed. This is not UDP. And as a result, you won't have toweling. You'll either have something to play or you won't have anything to play. One of the two. So now we turn to multicasting. Multicast IP. Where would I use multicast? Anytime you're sending a signal that's going to go from one source to a group of devices. Multicasting is one to many, one to a group. And you can use it in your network, but you can't use it in the internet. The reason is the internet doesn't support it. Why would I use it? Well, for one thing, it's going to reduce the overall usage. If you're doing unicast, every receiver has to have its own full stream. With multicast, that's not the case. Since we're not sending as many streams, we won't have to do as much processing in the server. And because we aren't transmitting as much traffic, we'll have less interference or less of an effect on other traffic. And finally, we can synchronize the time of delivery so that all of the different streams that are being sent, that is what appear to be different streams that are being sent, all appear at the same time. So multicasting works something like this. This is a very high-level view. Here I have a source that's putting out two streams. We'll call it the red program stream and a yellow program stream. And I have routers in the network that are multicast enabled. Now notice in this case that the red program stream is taking this path to its destinations, and the yellow is taking a different path. But on this path here, there's only the red stream because downstream from this router on this path, there's only one person or only one program being requested. There's also only one stream here. In other words, the number of streams on an individual link is the number of viewers for those streams matches the number of different streams being viewed downstream. These links over here carry no video because they aren't part of the path that leads to program viewers that are watching the yellow stream, yellow program, or watching the red program. So the bottom line is a link does not carry video unless there's a downstream device or viewer requesting that video. Now, reviewing quickly, we talked about this in the first webinar, but reviewing quickly, multicast IP addresses are addresses which begin with 224 to 239. Generally, one address is used per program stream. This down here is fairly typical. RF channel 1 is placed on 224.1.0.101. RF channel 2 goes on 102. RF channel 3 goes on 103 and so forth. Very simple way of keeping track of which is channel 1, channel 2, and channel 3 in the RF channel assignment. We could actually accomplish the same thing here if we changed the port number that was being used in the UDP header. But in my experience, I've only ever seen that done one time. Almost always, this is the kind of scheme that typically would be used. So how does the person choose in IPTV, how does the person choose the channel to watch? Well, in this case here, Sally sitting at the second computer over here is watching channel 2, and it's kind of a boring program. So she decides that she doesn't want to watch that anymore, and she picks up her remote and she hits the channel 3 button, and her set-top box or her smart TV sends a packet up to the router called a leave packet, leave channel 2. And when the router gets that, it stops copying the red channel down to her. The leave packet is dropped, and then she sends a join for channel 3 upstream. The router reads that, knows it has a copy of that channel, the yellow channel, and begins to copy the yellow channel, and now she watches the yellow channel. This is called zapping, or channel zapping. And most people who first experience IPTV complain that they don't like the way it takes so much time to do a channel zap. But you have to think about how the old traditional system worked and how the IPTV system works. In conventional coax systems, all of the channels were at all of the TVs all of the time. You simply tuned to a new channel. But in IPTV, we have to do this process where we say, hey, router, stop copying the old channel, start copying the new channel. And it's entirely conceivable that when the join comes up to this router from downstream, the router says, I don't have a copy of it, and it has to go further upstream to get a copy. So the time change here can be considerable. The industry standard recommendation is for this to happen in 2 seconds or less. VLANs can be extremely useful in multicasting networks. Multicasting is independent of the idea of the subnet, and multicasting can be done with a single VLAN or across VLANs connected by multicast-enabled routers. In this left-hand architecture here, if we have a mixture of data applications and MPEG transport, all of the traffic is going to be intermingled on this network, and there is no question that the video traffic that is in the network, because typically it takes a lot of bandwidth, is going to affect the data applications. And as I talked about in the second webinar, it will slow down those data applications, those TCP applications. In this architecture here, we can put all of the data applications on one VLAN, put our IPTV traffic on a separate VLAN, and this traffic over here and this traffic over here will not interfere with each other. This traffic over here, the UDP traffic, will not interfere with any of the data applications that are over here. The important thing to understand is there's no difference in equipment in the network here and here. It's how the network equipment is configured. We simply configure the switches differently to use 2 different VLANs. Now, one of the toughest topics to understand with multicasting is something called IGMP snooping. IGMP stands for Internet Group Messaging Protocol. And it's basically the standard for how multicasting is done. Snooping is something that you may have heard somebody mention or heard somebody say something about. Snooping is something switches do. And my experience has been that if people don't know when to turn it on, if they don't know when to turn it on and don't turn it on, it can lead to absolutely disastrous results. So I want to take a little time to give you enough information that you understand what snooping is and why snooping is so critical. I actually had a consulting client in the South, that's all I need to say about it, but they were in the South, and they didn't know to turn IGMP snooping on. And for nearly 2 years, this poor fellow used about twice the bandwidth in his switch network that he needed to use and was frustrated just beyond belief. And finally, after he sent me trace after trace after trace, it hit me. The reason I was seeing all the broadcast traffic was because either his switches couldn't support snooping or he hadn't turned it on. So I called him and asked him, are you using IGMP snooping? And he said, I don't know what that is. And I said, well, find somebody in the IT department, talk to them, get them to make sure it's turned on. And sure enough, when they turned IGMP snooping on, his problem that had been around for 2 years went away almost instantly. But to understand the concept of IGMP snooping, we have to go back and look at layer 2 and layer 3 addressing. Ethernet addresses are 48 bits long, 6 bytes, burned into the network interface card. All your devices on the network will have a NIC card with a 48-bit MAC address. The router interfaces will have a 48-bit MAC address. When addresses at the MAC level, at the Ethernet level, begin with a binary 1, they're considered group addresses, and they're typically sent to everybody in the group, or in the case of everyone being in the group, sent as a broadcast. Layer 3 addresses, layer 3 multicast addresses, are 4 bytes long. And as we said, they start with the first byte of 224 through 239. But the relationship between the MAC address, which is a 48-bit hardware address, and the IP address, which is a 4-byte software address, the relationship between those two for multicast networks is a little complicated. This is what the multicast IP address starts out like in binary. It starts out 1110 because it has to be at least 224, so in binary it has to be at least 111 and then 0. So we have these 4 bits, 5 rather random bits, and 23 bits that make up the rest of that address. What happens in multicasting is that the multicast device, the multicast-enabled device, puts in place of the beginning of the MAC address, it puts in hexadecimal 01005E. That's required by the IEEE standard. This is how you say a multicast IP address is being used. You put in hexadecimal 01005E. Hexadecimal 01 is binary 0000 001, 7 zeros and a 1. But when it's transmitted in the reverse order. I know that's a little complicated, but the bottom line is that the address that's sent out on the network as the MAC address of the destination is a combination of the IP and the MAC address. Remember that part. It's a combination of these two. It's not the multicast address, the IP address. It's not the MAC address that the device is going to get it, not in the NIC card of the device that's going to get it. It's a composition of these two. And we'll come back and see what importance that has. So let's talk about how switches work and how switches learn. The very first packet that I send through a switch goes to all ports. If A sends an Ethernet frame into the switch has no idea where B is. So it says, well, I don't know where B is, so I'll send it everywhere to broadcast it. When B responds, the switch learns that B is off of this port, and it now knows A is off of this port, so that from the second frame on, anything going from A to B goes in this port here and comes out the corresponding port out here, because that's all stored in a filtering table in here which keeps track of which devices are attached to which ports. So in a unicast, that is something being sent by one device like A to one device B, from the first exchange on, it goes in one port and goes out another port. If it's either a MAC layer, Ethernet layer broadcast, or an IP broadcast, it goes in one port, and it goes out all ports. Now, what we want to have happen, if you think about the green dot network that we were doing multicasting, with multicasting, we want it to go in one port and come out those ports where there is a downstream viewer. This is what we want to have happen. But let's step back a second. Look what happened when we sent a frame in and the switch didn't know the destination address. It came out all ports. It was a broadcast. Here comes a multicast frame. The destination MAC address has been modified. It's not a specific device on the network. So the first frame will come out all ports unless we turn on a feature that says, whoa, 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 whoa. I'll let that one go through, but I'm going to watch for a join coming back on this port. And if a join comes back, I'll now know that that's a multicast packet, and it should only go out that corresponding port. So the way the switch learns about this situation is it has to recognize a multicast address, and then it has to watch for the join coming upstream to determine which ports to send traffic out and which ports not to send traffic out. This is called IGMP snooping. Low-cost switches, and I don't mean any particular brand, low-cost switches typically do not support snooping, and your multicast traffic will be broadcast everywhere. More sophisticated switches with more sophisticated software, will know to have snooping available, and you can turn it on, and when you turn snooping on, you'll be able to basically stop the process of broadcasting packets everywhere. This is a fairly critical factor with multicast traffic. So when I want to set multicast up in the encoder, again, this is the same AdTech E100 encoder, I have to go to the IP transport tab. I turn on multicasting, and for these 4 program streams it can send, I pick the IP address that I want it to be sent to, and I decide the port that I want to use. I can use any port I want to, really, but port around 2000 is fairly typical. Here I can even indicate whether or not I want to use forward error correction, which adds a little overhead but will reduce the effective errors in some cases. And I do that for each one of the channels I want to transmit. Destination 1, Destination 2, Destination 3, where the destination is a group of devices, those people watching a single channel. In the decoder, this is the RD70 AdTech decoder, all I really have to do is tell it, what is the packet structure like? Here we're using RTP, UDP and RTP. We're receiving UDP and RTP. What address am I watching for? I'm watching for this address. And really, what port am I looking for? Those are the 3 critical factors here. What's the packet structure? What's the IP address? What's the port number? And we have the decoder set up. That's the end of my presentation on multicasting and IPTV. I've enjoyed doing this webinar series for Starin, and I hope to get to work with you in the future. I hope these sessions were beneficial to you. So now I'll turn it back over to Neil.
I know they were definitely beneficial for me. This was one of my favorite ones, that's for sure. You know, when I was in college, I pretended that I liked Radiohead because I thought it might make me more attractive to the artsy girls, and I can tell you that it didn't work. But I'll tell you this, Cheryl Simmons is not a pretender, because she was the one that identified an original member of Radiohead without mentioning Tom York, who I think is probably the one everybody knows from Radiohead. So congratulations, Cheryl. Way to go. Thanks to everybody for attending. You really make our day here at Starin. You know, the business climate is changing, and AV over IP is going to become the norm, if it isn't already. If you're listening to me right now, of course, you understand that, because you realize these workshops can help you prepare for this future. Is your company ready? So that's why we're having our AV over IP immersion camps throughout the U.S. this summer and fall, the first one being July 28th, 29th, and 30th in Cincinnati, Ohio. So we'll make sure that you're ready and your company is ready. And we'll also be sending out a flyer to you, to everybody that's attended today, to show you the background story on each of these AV over IP immersion camps. Remember that, you know, there's labs, so there's going to be plenty of hands-on, and it's, again, I say, it's Professor Phil in person for a 3-day immersion. So we'll keep you posted of any upcoming AV over IP immersion camps. Also, don't forget our AV Meetup coffee breaks coming up. First one we have coming up is Friday, May 22nd, and it's going to be browser streaming distribution with Wowza. So don't miss that one. And again, that's a 20-minute. So sit back with your coffee and learn about browser streaming distribution. So I want to make sure that we're answering everybody's questions, and we have give everybody enough time to title in their questions. So we have a few of these here. One question is, can we access the recordings of these episodes somewhere? Yes, we'll send you a link to where you can find the recordings of these when you write, not too long after we all hang up today. One question is for Dr. Phil, how does an IP query function?
IP querying is part of the IGMP process, and it is where essentially the routers take an active, a kind of proactive, I guess you'd say, stance to see what programs are available. In other words, rather than waiting for a particular join to be issued, it will announce that I have the following programs available. So querying is something that speeds up the process of getting join leave process. How do I want to say this? The time it takes to do that is improved.
Gotcha. Also, if you look in the chat window, you can see the recordings of these past sessions at www.staren.biz/AVoverlP. Here's a good one. Where do you see IPTV being used, Professor Phil?
It's just been, within about the last year and a half, it's been introduced into digital signage. And digital signage itself is an area that's growing. I think that's where it's going to see its biggest increase in use. Although, it wouldn't surprise me to see systems come out that are hybrid systems that are a mixture of streaming over HTTP and IPTV, where, for example, one part of a program sequence is delivered by IPTV, and there's kind of a break, and it switches over and begins to show what's being streamed through adaptive streaming. There's certainly nothing in the technology that keeps that from happening. Right now it's a question of what people are manufacturing. And by the way, the use of RTP in IPTV, whether or not that's used, it's not dependent that much on the breakdown of carrier versus enterprise. It's broken down by who builds the equipment for the carriers and who builds the equipment for the enterprise. Those who build it for the enterprise typically don't. They make RTP available, but by default it's turned off. But those people who are building equipment for enterprise applications by default usually turn it on.
So you're saying it's starting to get pretty extensive.
It's being used more and more and more.
Yeah.
For quite some time, even implementing multicasting was difficult, but because it's getting easier and easier to get through the screens and implement multicasting, that's always been the big hang-up with IPTV, is establishing the multicast network and making it work. But people are finally figuring out, one, put it on its own VLAN, two, turn on IGMP snooping, make sure your switches support that, and the rest is pretty easy. Configuring the encoders and decoders is fairly easy.
Someone added from the audience, how about in hospital patient rooms?
That's the primary application right now in hospitals.
Gotcha.
Most of the hospitals I've worked with mix together what I would call training streaming. This is how you give yourself a shot, together with Oprah on TV and the evening news, and they mix that in with screens that are coming from basically a software system and application which allows you to pick tomorrow morning's breakfast foods. So yeah, it's targeted towards the patient room. The key there is to have a good middleware company. Somebody has a good management system. That's the real key.
So how much does it take to get it put into a system?
How much does it take? How much money does it take?
Yeah, I mean, what would it take to get into a system?
That's a good question. And like so many different things, the price varies all over the place. If I want to run, let's say, 40 channels of video to 200 patient rooms, I'm probably going to need something that will do a total of 40 individual multicast IP channels. So probably $35,000 to $75,000 for the encoding devices. Probably use set-top boxes attached to standard TVs. Think $80 to $120 per set-top box, and then the cost of the middleware to manage it. So we probably are looking at some place between $150,000 and $300,000 total.
Gotcha.
Just pulling those right out of the hat.
Yeah, no, I understand. There's another question. Is it possible for a router to convert unicast to multicast or multicast to unicast, or is a special device required like a server?
No, routers are not going to make a conversion like that. They're going to read the address and say this is a unicast, or they're going to read the address and say this is a multicast. They're not going to make the change. If you need the stream changed from unicast to multicast, for example, you might unicast it to a CDN and then multicast it out of the CDN, come out of the CDN, and then multicast it across your network. You're going to transcode it. And when you transcode it, you're rebuilding the packet. And you can change the addresses any way you want to do it. So the answer is yes. You'll go through something similar to a server. You'll go through some kind of a device that's able to rebuild the packet.
All right. We have Wowza could also be used for transcoding and
yes, yes, that's a good application. Yes, almost all of the companies like Wowza are now taking streams in. They can accept a transport stream in. They can accept an SDI stream in, a composite stream, whatever kind of stream you want to feed in, and they'll send it out just about any way you want. They'll send it out IP multicast, or they'll send it out adaptive stream, or just about any way you want it sent out. They're doing your transcoding.
Right. Right. And remember, next Friday, we're going to be covering Wowza in our coffee breaks. Could you comment on which is better, hardware decoders or software decoders? Hardware decoders or software decoders?
There is no general pattern except to say more and more and more vendors are leaning towards software because they are so easily adapted and so easily updated. But the day of hardware decoding outperforming software decoding, it has long since passed. They're on par with each other now.
Can we use the existing TVs that are Poridian enabled? Am I pronouncing that correctly? You mean QAM TV?
I think
that's it out.
If that's a question, yeah. The set-top box is going to make the conversion from IP into whatever you want, into composite or QAM or whatever.
Okay.
Yeah, that's the role of the set-top box.
Okay, thanks, Professor Phil. And sorry, Al, that I bobbled your question there. Here's a good question. What are the steps for putting in IPTV? Are there stages to getting it going?
Well, it depends whether there is an existing system in there. If there's an existing system in there, and let's say there's an existing coax system in, then you're going to have to design your encoder end based on the kinds of inputs you're getting from carriers or players or whatever sources, what your video sources are like. And if you had coax and you didn't have twisted pair, which is rather unusual, but if you had coax and twisted pair, then you had to recable. But today, when you recable with something like Category 6, it's going to serve virtually every purpose that you're going to need for the next couple of decades, we think, at least. The decoding end is actually a little bit easier because on the decoding end, the only thing we have to worry about is picking the right kind of set-top box, typically. And set-top boxes aren't that terribly expensive. They've come down in price quite a bit. Just ballpark ideas, $75 to $150 will get you just about any set-top box you need for any kind of application. It's really the critical thing is to look at the source end and look at what kinds of sources you have and whether or not you already have an existing cabling structure or have to replace that. But always, 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 if you're going to deploy MPEG transport IPTV, look at the middleware and the skill of the middleware vendor, because the management system is going to, more than anything, determine your happiness with the overall system.
There's one more question. What is the max resolution that one can send over IPTV?
What is the max resolution you can buy a source? There's no limit.
All right.
Remember, this is just data that we pack inside of an IP packet. You want 4K? You can get 4K. MPEG transport is based on the MPEG compression algorithms, and so anything that can be compressed by H.264 HEVC, anything that can be compressed can be packed in an IP packet, so there's no upper limit.
Just to take a couple steps back, AdTech has middleware. Is there anybody else that has middleware?
It depends on whether you're talking about schools or hospitals, but with hospitals, there are probably 8 or 10 different vendors that specialize in, they try to gain their value add based on the efficiency of presenting patient information more than the ability to manage your IPTV system. In other words, managing whether or not you can get CNBC on the patient's television system, that becomes secondary to what you can present in terms of hospital billing, admissions, and those kinds of things that are part of the business system. The business system is always first in the middleware, and then the management of the MPEG transport system is secondary.
One question, in a video-intensive IP network, what should we look for spec-wise in a multicast switch?
I would say that's probably a non-issue. For the most part, almost all switches today, their switching fabric is fast enough that they can stay up with virtually any rate that would be coming in the input ports. Very, very few switches today are what we used to call blocking switches. In other words, they can only handle a certain level of traffic. If I have a 24-port switch, it can have 12 data paths through it, one input, one output. If it's a gigabit switch, I only need a 12 gigabit backplane. That's almost trivial today. So they put a 15 gigabit backplane in it, and no packet ever gets blocked. So the speed with which a switch performs is probably not an issue today. And I see the difference between the choice in switching being much more one of what is your staff comfortable with. Is your staff comfortable with the Cisco operating system? If they aren't, stay away from them. If they are comfortable with Cisco operating system, probably stay with them because they're familiar. But I think there are almost cultural kinds of issues there as opposed to technical performance issues.
Thanks again to everybody for joining us. You really, really make our day, and we're very, very pleased with this session. Thanks to you, Professor Phil. Well done, as always. Make sure that you look for us on the 22nd for our next AV Meetup coffee break. Spend 20 minutes with us and learn some cool information. Thanks again to everybody for joining us. Have a great day and have a great weekend. Take care.